Okay. The teacher holds up two bottles containing different liquids. The liquids have different densities and do not dissolve in each other. One liquid is water and the other liquid is vegetable oil. She then adds iodine crystals to the bottle. Describe what the bottle now looks like. Draw a picture of what happened to the water, oil, and iodine. Explain what you observed using the words polar and nonpolar covalent. All right, so my picture is going to look like this. So I'm going to put my oil up here and my water down here. And I know that this is polar covalent and this is nonpolar covalent. So the question is, where is the iodine going to end up? Well, iodine and all diatomics are nonpolar covalent, right? They're symmetrical. There is no central atom, so there's no charge disparity here. So where's it going to end up? It's going to end up in the oil here, right? And it's because it is nonpolar covalent and oil is nonpolar covalent. Different bond types have different, I could write it all out. I observed the iodine dissolving in the oil, whatever. I'm just going to use words instead of writing. So yeah, I would throw my iodine into my bottle and it would dissolve in the oil because it is a nonpolar covalent. It is both symmetrical, there is no central atom, and there is no charge disparity. So different bond types have different physical and chemical properties. Explain why salt water conducts electricity. Pretty easy. NaCl, which is salt, is an ionic compound. So when it goes into water, it breaks down into its Na and Cl bits. OCD is getting the best of me. So I have my negative and positive. That means that there's a charge disparity, which means electricity can move through it. While it's combined together, while it's dry, this has zero charge, right? This compound, this NaCl. But when I put it into water, it breaks into its common ion, it breaks into its ions, and now there's a chance for those electrons to move through the water. Same thing happens if I have a furnace hot enough to melt salt. It'll break up into its fundamental ions. They will move so fast that they can't really hang out together, and electricity can then move through it. It's called a salt battery. In order of bond strength. Okay, so we have metallic, and then ionic, and then covalent. That's just a memorization thing. You're going to have to memorize that little chart I did on the bottom of the first page, or where did I do it? Back of the first page. Yeah. You're going to have to memorize this. You got to know this. All right. Rank the following intramolecular forces in order of increasing bond strength based on the property below. Here's the problem that I have. I think what they meant was intermolecular. Because if I'm testing viscosity, or I have to know the bond type before I know the viscosity. Which syrup, you don't know that. Water, we know that this is a polar covalent. Covalent hydrogen bond. Oh, they're asking to point out. Okay, I'm not even going to go into this. This can hydrogen bond because it's got oxygen. Syrup, you don't know, but let's say it's sucrose. And oil is nonpolar covalent. So this is going to be, I guess, CHB, hydrogen bond. And this is, what are they saying here? I don't get what they're saying here. This is idiotic. How about we just do this? We rank the intermolecular forces based on the viscosity, because that's really going to be the most important. So strongest intermolecular force, second strongest, third strongest. If it takes longer to pour, like syrup, then it has a stronger intermolecular force. I don't know why there's no ionic. Never mind. Anyway, that's the rank, and it's due to the test of viscosity. That's the test we use to test intermolecular forces. Viscosity is resistance to flow. Resistance to flow. You'll have to forgive my spelling. When in a lab setting, what would be a good way to check the type of bond your unknown compound possesses? Circle your choices. Okay, so melting point would be a good one. Boiling point would be a good one. If we're just talking about intramolecular bond, then I'm going to use, no, it's got to be intermolecular bonds that we're checking, right? Well, you can use melting point to test intramolecular. But yeah, I'm not going to use well, you could use solubility, because that would tell you whether it's nonpolar or polar covalent. So you could use solubility in oil and water, viscosity, boiling point, and melting point. Those will all work. What am I looking at here? Okay, let me see. Where am I at here? Okay. All right. You could actually use volatility, but we didn't talk about it much. So, draw a picture of ionic, nonpolar, and polar molecules using circle. Okay, so this is yeah. So this is my picture that I drew before. So ionic is just the two balls, and then polar covalent is the big peanut kind of thing with a partial negative, partial positive charge, so you can, and then the football, non-polar covalent, polar covalent, ionic. So I drew the pictures. Okay. Hopefully you can see those, and hopefully you'll memorize them. There's a few questions on the test that use these pictures. What is the difference between an intermolecular and intramolecular? Show these using water. Okay, well, I've drawn it a couple hundred times. That is intra. That's inside of a molecule. And then I'm going to show two water molecules interacting with each other. And this dotted bond, that is inter. Certainly didn't leave me much room to answer this, did they? Okay. What test can you perform for intermolecular force strength? Well, that's viscosity tests. And what test can you perform for intramolecular? None. 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 Explain how water has both a polar bond and a polar molecular structure. Okay. So, it has a polar bond. That bond is polar because oxygen has a very high electronegativity. So, it's not really sharing this electron. It's pulling it more over here than it is over here. So if this is a line, then, and instead of sharing perfectly in the middle, we're going to say that it's towards one end. So that gives this a partial negative charge and a partial positive charge. That's the polarity in the bond. The polarity in the molecular structure, we've got these negative charges here. So this creates a partial negative charge for the whole structure, and this creates a partial positive charge for the whole structure. It is not symmetrical. It has those lone pairs, so we know that it is a polar structure as well as a polar bond. I don't like them when they break them apart like that and discuss them as two different things, because the reason this is a polar structure is kind of similar to the reason it's a polar bond. What is the product of fluorine and iron 3 chloride? Okay, so I have fluorine plus iron 3 chloride. Now remember, this is plus 3, this is minus 1, so I got to crisscross. And they're going to trade places. So who's going to trade places? This is a cation, this is an anion, fluorine's an anion. If when in doubt, iron, anything that's a metal is a cation. Chlorine, right here, -1. Fluorine, right here, -1. So I have one cation and two anions. So who's switching places? Well, that iron is going to stay the same, and these two are going to switch. And again, the subscripts don't travel. Oh, by the way, that's F2. Sorry. I forgot my diatomics for a minute. You should slap me for that one. Okay, subscripts don't travel, but this is a diatomic, so it has to have a 2. This is charged plus 3, this is minus 1, so this has to have a 3 by it. And then you'd have to balance this, so I need 2 of these, and 3 of these, and 2 of these, and 3 of these. So it'd be a 3, 2, 2, 3. What happened to the electrons in the potassium and chlorine atoms? What? You didn't say anything about potassium and chlorine, but if we have to, we would draw it again and say they transferred to the chlorine. They transferred to the chlorine, right? This is positive. The reason it's positively charged, the reason potassium is +1 is because it wants to lose that electron. Chlorine wants that electron, so it transfers it. Students performed a lab in class and obtained the following data. Which is a correct conclusion based on the data presented? I wish these were all on one page. So hard. Okay. So, now we're answering questions. All right. These are what the questions look like on the test. So substance A is a solid at room temperature, so it could be ionic, nonpolar, covalent, covalent. It's soluble in water. That means it's going to be ionic or polar covalent. So this is how I would answer it. Substance B is a solid, and it dissolves in water, so this is ionic or polar covalent. Substance C is a solid, dissolves in water, ionic, polar covalent. Substance D is a gas, and it does not dissolve in water, so this is probably a non-polar covalent, right? Non-polar covalent, a lot of gases there. Okay, the student has sufficient data in order to determine bond present in each substance because only polar covalent bonds are soluble in water and only non-polar covalent substances are gases at room temperature. Okay, the student needs more information in order to classify. Well, that's kind of what the first answer said. The student needs more information. So really, I can't break these down beyond ionic and polar covalent, can I? So this has to be B. Well, let's keep reading. So I'm going to mark A off. The student has sufficient data. Well, no, they don't. Student needs more information, so this is a question. The student has sufficient data in order to determine the type of bond present in each substance. The bond type, because both nonpolar and polar substances are soluble, that's a lie. Whenever you read something that's a lie, just mark it out. The student needs more information in order to classify the bond type because both ionic and polar substances are soluble in water. That's true. Both are solid at room temperature. That's true. Because only nonpolar covalent bonds are soluble. What? And our gases at... This makes no sense. Needs more information because both ionic and polar substances are soluble in water. That is absolutely true. And are solid at room temperature because only nonpolar covalent bonds are soluble in water. That I don't even know. That's worded so terribly I don't even know what to say. So I'm going to say B is the answer. But in this case, I would call me over and I would say, Mr. Irwin, what are they asking here? Or what are they saying? Student needs more information to classify the bond type because both ionic and polar substances are soluble in water, comma, and both are solid at room temperature because only both are solid at room temperature because only nonpolar covalent bonds are soluble in water and gases. That's not even a sentence. I would spurn that answer because it's not even a sentence. So yeah. So this is just like the test then.